You ever been out on a walk, picked up a cool looking rock, and just wondered, what is this thing? You know, where did it come from? How old is it? Well, guess what? You're not alone. And today, we're going to dig into those exact questions. We're going on a journey deep into the ground beneath our feet, from the tiniest grain of sand to the biggest mountain. So let's get into it.
So let's just start with that big question right there. If you could zoom in on any rock, I mean way in, what would you actually see? It's not just some solid lump. Turns out it's actually this incredible mix of different ingredients all locked together in a fascinating way.
And those ingredients? Well, they're called minerals. The best way to think about it is like this. If a rock is a cake, then minerals are the flour, the sugar, the eggs. They are the absolute fundamental, pure building blocks that come together to create every single rock on this planet.
Okay, so to really get this, we've got to put on our geology detective hats and zoom in even further. We're going to trace the whole assembly line, right from the invisible little atoms that start it all to the solid rock that you can actually hold in your hand.
Now, this is where it gets really cool, because this lays out the whole construction process. It all starts with the tiniest things, atoms. When you get a bunch of the same atoms together, they form elements, like on the periodic table. Then, those elements combine in these really specific structured ways to form our building blocks, the minerals. And finally, you mix one or more of those minerals together, and boom, you've got a rock. It's this perfect four-step pyramid.
So, there are rules to this game. Not just anything gets to be called a mineral. First, it has to be naturally occurring, so no lab-grown diamonds. Second, it's got to be inorganic, meaning it didn't come from plants or animals. And this is the really wild part. It has to be a crystalline solid. That means its atoms are locked into this perfect, repeating 3D pattern. And that pattern is what gives every mineral its unique shape and all its cool properties.
And get this, there are over 3,800 known minerals out there. But, and this is the key, the vast majority of rocks you will ever see in your life are made from just a handful of these common groups. The most important ones, by far, are the silicates, which include stuff you see every day like quartz. So the takeaway is pretty simple. The mineral world is huge, but the building blocks for most rocks come from a very small club.
All right, so we've got our ingredients, the minerals. Let's start cooking. Our first recipe is for igneous rocks, and these are the ones that are born from the crazy, intense heat deep inside our planet.
The idea here is actually pretty simple, but it's super powerful. Deep down in the earth, it is so incredibly hot that rock actually melts. We call that molten rock magma. And when that magma cools down and hardens, either way deep underground or after it erupts from a volcano as lava, it becomes an igneous rock. And what's so cool is that how the final rock looks, its texture, it all comes down to one thing: how fast it cooled. If the magma cools really slowly, deep underground, the mineral crystals have tons of time to grow big and beautiful. Geologists call that a phaneritic texture. Think of a granite countertop. You can see all those big, sparkly crystals, right? But if it shoots out of a volcano as lava and cools in just a few days or hours, the crystals stay microscopic. That gives you a fine-grained, aphanitic texture that's really smooth. Okay, on to recipe number 2. This one isn't about fire and heat. This one is all about time, pressure, and a whole lot of recycling. We're talking sedimentary rocks. I love this idea. These rocks are literally made from the planet's leftovers. You've got wind, water, and ice that are constantly beating down on older rocks, breaking them into tiny pieces. We call those pieces sediment. So the sand on a beach, the mud at the bottom of a lake, sedimentary rocks are what happens when all that stuff gets glued back together into a whole new rock. So how does loose sand turn into solid rock? It's a process called lithification, and you can think of it like a 3-act play. Act 1, accumulation. Layers of sediment get dropped off, piling up over time. Act 2, compaction. The incredible weight of all the new layers on top squeezes all the water out of the bottom layers. And for the grand finale, Act 3, cementation. Natural minerals that were dissolved in the water crystallize and act like a superglue, binding all those little grains together. And voila, you have a new rock.
All right, our final recipe, and this one is the most dramatic of them all. It's not about making something new from scratch. It's about a total transformation, a rock makeover, if you will. This is where you take an existing rock and put it under such extreme heat and pressure that it becomes something completely new. This is the metamorphic recipe.
Now, this is super important. The original rock doesn't actually melt. If it melted, well, it would just become magma, right? And we'd be back to making an igneous rock. Instead, it gets baked and squeezed so intensely that the minerals inside it literally change and rearrange themselves into a new structure. So what kind of forces are we talking about here? We're talking about being cooked by nearby magma, being crushed by the weight of entire mountains sitting on top of you, and maybe the most powerful of all, being squeezed in one direction by the unimaginable force of continents crashing into each other. And that directed pressure from plate collisions, it creates one of the coolest looking features in all of geology. It literally forces the minerals to line up, creating these awesome bands or layers in the rock. We call that a foliated texture. Now, if a rock is just baked by heat without that directional squeeze, it ends up looking more grainy and uniform, which we call non-foliated. Okay, so we've got our three main characters: igneous, sedimentary, and metamorphic. But here's the plot twist. They're not separate stories. They are all connected. They're all part of one giant, continuous cycle that has been shaping our planet for billions of years. That granite countertop in your kitchen? That sandstone building downtown? On a geologic timescale, they're just passing through. Every single rock is destined to be broken down, reformed, and transformed into something else entirely. This right here, this is the whole secret. It's what we call the rock cycle. It's the ultimate recycling program on a planetary scale. An igneous rock can be worn down into sand, which becomes a sedimentary rock. That sedimentary rock can get buried deep down and transformed into a metamorphic rock. And if that gets dragged even deeper, it can melt back into magma, ready to start the whole cycle all over again. And this journey is just endless. You can jump in anywhere. Magma cools, you get igneous rock. That rock breaks down, you get sediment. That sediment gets squeezed and glued into sedimentary rock. That rock gets buried, heated, and squished into metamorphic rock. And if it gets hot enough, it melts right back into magma. And around we go. So what's the engine driving this massive planetary recycling plant? What keeps it all going? The answer is the slow, relentless movement of the Earth's tectonic plates. That is the engine that drives every single thing we've just talked about. Just think about it for a second. When plates smash together, what happens? You get mountains. And what happens to mountains? They erode, making tons of sediment for new sedimentary rocks. When one plate dives under another, that's called subduction, it drags rock deep into the Earth, where it gets cooked, metamorphosed, or even melted completely into new magma. Plate tectonics is the master architect here. So you see, it's not three different processes for three different kinds of rocks. It's one single, beautiful, interconnected system. One grand story that explains how the surface of our planet is constantly being built up, torn down, and remade from the inside out. And that just leaves us with this one kind of mind-blowing thought. This cycle, it never stops. The mountains, the oceans, the continents we see today, they're just a snapshot in time. So if we could fast forward way into the future, what do you think our world will look like in another 100 million years? What new mountains and new rocks will this great recycler have created? Definitely something to think about the next time you pick up a simple stone.